Okay, so there was a question about resonance as well as formal charge. These are actually two separate things. I think sometimes they get confused because a lot of the examples that we use for formal charge also contain resonance. The other thing that gets confused is things that contain resonance, do they have to have a charge? Like, do they have to be a polyatomic ion? And no, that's not the case. So let me just give you a couple of examples of resonance, and then I'll probably do a separate video for formal charge just to keep them distinct and separate. Okay, so resonance is any time that we can draw equivalent structures where in our limited understanding of it, it's just where a double bond can be moved, and we need to represent that because the two different options, the real molecule is like a, or two or three, whatever. The real molecule is an average of those structures that we're going to show. Let me do an example because obviously that'll make more sense. Let's do the sulfate ion, and then we're also going to do ozone, which is O3. So this will be a good reminder of drawing Lewis structures as well, just in case anyone else needs that. So 1, 2, 3, 4, 5, 6. 6, okay. And then oxygen, 1, 2, 3, 4, 5, 6. I'm just going to copy and paste that. Copy. Okay, so 4 oxygens. And then don't forget that 2- charge means we have 2 extra electrons from somewhere. So I'm just going to tack those on, like, let's say these side oxygens, okay? So now I need to draw the bonds. So I'm going to connect things. So they always look wacky when I do this, but like there's the unpaired electron here, and we'll connect it to this unpaired electron. That's a bond. Same thing here. We're going to take this one unpaired electron and connect it to that one. Okay, so pretty quickly you see that you don't have any more unpaired electrons on sulfur, but you know you need to bond the oxygens. You also know that you need to fill their octet. So we're actually going to have to connect both of those. So sulfur will not have any lone pairs. So redrawing that, we've got a double bond to 1 oxygen with 2 lone pairs, another double bond to 1 oxygen with 2 lone pairs, and then a single bond to oxygens with 3 lone pairs. Okay, so taking this structure, oh, and we got to put those brackets in because this is a charged species. We have to remind everybody of that. Now, when we look at this structure, all of these bonding regions actually have a bond order of 1.5. Okay, the bond energy, the bond length, all looks like a 1.5 of a bond. So somewhere between 1 and 2 as far as its length and its energy, like how hard it is to break. So the reason for that is because this isn't, in and of itself, it's not the best structure. Because what really happens is these double bonds get spread over all 4 of those regions. This is what's called delocalization. It's the electron charge spreading over all 4 of those regions. And, sorry, that happens because they're equivalent. It doesn't matter which oxygen it's tied to. So the way we have to represent that is that we have to show all of the structures, and I'm going to copy and paste again. We have to show all of the structures that potentially could be represented here in order to indicate that that double bond could spread over multiple regions. Now, for this one, you have to remember that those 4 oxygens, they're like, it doesn't matter that we've drawn them, you know, across from each other. The geometry of this is actually tetrahedral and stuff. They are distinct separate oxygens. So we're going to have to draw the double bond being in multiple. I guess what I'm saying is that it doesn't matter that they're right across from each other. You know, we can draw another one where they're right across from each other. That's another resonance structure. But we can also draw them whereas one is, each of them are next to each other. Now, I'm going to go back and fix the lone pairs, because wherever there's a double bond, there have to be 2 lone pairs, and wherever there's a single bond, there have to be 3. Otherwise, the octet wouldn't be satisfied and everything. So there's the third pair rather. There's the third pair. And then down on this one, that needs a third pair, and we're going to erase those. Similarly over here, erase those and give this its third pair. Okay, so all 4 of these structures with these double-headed arrows in between them, if you were asked to draw the Lewis structure for SO4 2-, you would have to draw all 4 of these possibilities with those arrows between them to accurately represent the structure, because the real structure is an average of all 4 of these. And hopefully you can see, if it's an average of all 4 of them, why the bond order is 1.5. You have 6 bonds, 1, 2, 3, 4, 5, 6, spread over 4 regions. So 6 over 4 is 1.5 per region, or a bond order of 1.5. Okay, that's a pretty complicated example. Maybe I should have done ozone first, but we'll go ahead and do that now. Okay, so 6 electrons on each of these. So this is like ozone that's in the atmosphere. In the upper atmosphere, it's protective against UV rays. In the lower atmosphere, it's actually a pollutant. Okay, so I'm going to connect these guys up. So 1 bond there, 1 bond here. But our octet isn't satisfied yet for either of the outer oxygens. So something's going to have a double bond. But remember, oxygen can't overfill. So what really happens is, like, one of these electrons is going to pair up, it's going to move over here to satisfy that octet, and then the other one is going to pair up. Now, it's funny because, like I said, these are good examples of looking at formal charge too. So I'm not going to talk about that right now because I don't want to confuse the points, but I'm going to take O3 on the next video and talk about formal charge. Okay, so redrawing this structure, I've got oxygen on this side with a double bond, and then I have, looks like just 1 lone pair on that middle oxygen, and then I have a single bond to this oxygen with 3 lone pairs. That's the only way I can draw that structure, satisfying the octet for oxygen. And remember, oxygen is one of those things that has to have its octet strictly satisfied. So now I'm going to draw the other option. So I'm going to use those arrows to represent that this is a resonance structure. So the other option is with the single bond on this oxygen, and then the double bond over here. So this one's a little easier. It's just represented by these 2 resonance structures. The bond order, again, is 1.5 because it's 2 regions, but 3 bonds. So I think the only example we did maybe was CO3 that had 3 regions, but 4 bonds. So that would have been 1 1/3. Maybe it was CO3, maybe it was NO3-. I can't remember. Anyway, so that's resonance structure. So